This module briefly overviews the dynamics of the initiation and propagation of the Madden-Julian oscillation. A full treatment of this topic is far more than we can discuss in just one lecture. However, some major points are covered in this video. The fundamental features of convection associated with the MJO are listed here. The MJO is large in spatial scale. The circulation anomaly of the MJO projects strongly onto wave numbers 1 and 2. The convection in the MJO propagates only eastward and with a mean motion of about 5 meters per second, although the circulation signal can move much faster when not strongly coupled to convection over the Indo-Pacific worm pool. The periodicity falls within the subseasonal time range, but the MJO is irregular, with precipitation peaks occurring at various intervals. Sometimes, more MJO convective events more evenly spaced in time are clearly linked to a prior event, however others are not. This is part of the discussion we'll have during our paper discussion for this week. A major open question concerns how convection in the MJO develops in the first place. We know from many prior modules that the depth of convection is sensitive to moisture concentration in the lower free troposphere. If dry air is entrained into buoyant updrafts, the updrafts are diluted and eventually lose all positive buoyancy. However, convection is a major process through which moisture is transported out of the boundary layer and into the lower free troposphere. In the MJO, moisture is observed to increase in the troposphere in concert with the deepening of convection, as shown in this figure below, where the green shading sort of represents humidity anomalies and the depths of the clouds are represented by just how tall these cloud emblems are. When averaged over many MJO events, this slow buildup of moisture and convection can occur over a 2 to 3 week long period, over which the SST tends to increase at first while convection is generally suppressed, although observations indicate that this process often happens much more quickly. One major question involves how the moisture gets into the free troposphere. Does it get horizontally advected there, thus allowing convection to then subsequently develop, or does it get transported by clouds upward, allowing for subsequent clouds to grow deeper and transport moisture to even higher levels? The progression of moisture anomalies through height with a passing MJO is illustrated by the plot here, which is similar to the vertical structure plots we saw for other convectively coupled equatorial waves in a previous module. Dark shading in this plot indicates positive anomalies of specific humidity associated with the MJO. The anomalous OLR in the MJO is shown at the top, with a negative anomaly here indicating convection and a positive anomaly here. So we're compositing relative to a point where the MJO is most active at about 160 degrees east in longitude. Note that the x-axis here is shown as longitude and not time. The largest positive anomalies of humidity are located in the middle to upper troposphere at the same time the OLR anomaly is at its minimum, or essentially at the same longitude. However, the largest specific humidity anomaly in the lower troposphere is located to the east of the longitude of the OLR minimum. This is another example of how the humidity field is tilted with height in an equatorial wave. In this case, it's tilted westward with height. And the tilt does have some similarity to an eastward propagating gravity wave, where shallow convection is coincident with positive moisture anomalies ahead of the maximum upward motion anomaly, which would occur right here. While deep convection and stratiform precipitation is prevalent where these moisture anomalies extend into the upper troposphere. And mainly in the far upper troposphere, the moisture anomalies are really a manifestation of convection having pumped the moisture to that altitude. For an eastward propagating disturbance like convection in the MJO, this figure suggests that the humidity anomalies are first experienced in the lower troposphere and then aloft as convection transports the moisture upward. Additional evidence for this can be seen in time series of vertical profiles of relative humidity derived from Ransonde data. Green areas on this plot denote times and pressure levels where humidity was high, while red indicates dryness. Each row represents a time series at a different location in the Indian Ocean. This set of time series spans two MJO events that started in mid-October, about right here on the x-axis, and mid-November, about right here on the x-axis. Prior to both, a dry troposphere tops a moist boundary layer. It's particularly true here in October. At some point, high values of relative humidity are suddenly present, up to about 500 millibars, around the level of a climatological region of stability in the tropics that we've discussed in a previous module. After a few days of that, convection was able to penetrate this layer and deposit moisture deeply throughout the troposphere. At this point, we would say that a MJO was convectively active. This stepwise progression of moisture, we can see it in other MJOs and in other panels as well, strongly indicates a close linkage between clouds and moisture. Although this doesn't prove the arrow of causality between clouds and moisture, and that relationship will be further examined in our paper discussion for the week. Radar, combined with rayon sun data, suggests that convection leads the moistening of the troposphere. By analyzing moisture at various levels from the rayon sun data, the presence of convective and stratiform radar echo from the radar data, we're able to lag correlate deep convection and stratiform with tropospheric moisture. In this table, the decimal numbers indicate a maximum lag correlation between the variables listed on the left, and bolded values are statistically significant at the 95% level. The numbers in the parentheses here indicate the times at which the lag correlations were highest, and a positive number indicates that the variable in the first column precedes the variable in the second column. The different columns under a smoothing interval just show results when the time series are smoothed at various levels. Just focusing on this third column, or the first one under a smoothing interval where there's no smoothing used, we can see that at spatial scales of a radar, convection and 850 millibar humidity anomalies are nearly coincident with each other. They correlate with the coefficient of about 0.45 and the maximum correlations at a lag of 0. But the 300 millibar humidity lags the convection by about 9 hours. Stratiform precipitation occurs after the convection with a strong correlation and is more coincident with the humidity field at 700 to 500 millibars. This type of analysis strongly supports the notion that the convection leads to the humidity, at least on short time scales and small spatial scales represented by this type of data. There is scale similarity between this process and the relationships between these variables in the MJO, although in the MJO the lag periods are much longer. Combined with other analysis that we don't have time to show here, this points to a strong contribution of clouds in moistening the environment sufficiently to allow deep convection in the MJO to become established. This is required before the circulation in the MJO can become fully coupled with diabatic heating in the deep convection. In this week's paper discussion, we'll discuss the potential role of circumnavigating waves in allowing the growth of shallow convection and subsequent moistening of the lower troposphere. However, any process that leads to the large-scale moistening of the lower troposphere over a large region of warm SSTs, where convection can be sustained for many days, could potentially kick off a strong MJO event. What we just reviewed was related to the process of MJO initiation. That is, the transition from a period of convectively suppressed conditions over the Indo-Pacific to an active period. A problem that has, as of yet, been mostly treated separately is the maintenance and propagation of an existing MJO signal once convection in the MJO has been established. Taking a look again at the wave number frequency power spectrum of tropical OLR, we recall that a peak in power existed at very low frequency and mostly small wave numbers, with a peak at wave numbers 1 to 2. This partially aligns with the Kelvin wave, but is distinct, although with consideration of mean westerlies can be shown to be continuous with the Kelvin wave part of the spectrum, but that's a topic for a more advanced discussion. Next, we'll review one possible theory that explains MJO propagation. It is known as moisture mode theory. It begins with the assumption that weak temperature gradients exist in the tropics and uses moisture only as the prognostic variable. Unlike the dry Matsuno modes we discussed previously, the moisture mode theory incorporates moisture and describes MJO growth and propagation as being dependent upon the interaction between moisture and the MJO circulation. While we won't discuss this in great detail, the dispersion relationship for the MJO, when making such assumptions, is seen here at the top right. It is dependent upon the horizontal wind field, distribution of moisture horizontally, and the gross moist stability, which is the last term in the dispersion relationship. The gross moist stability is described as being dependent upon a term that is related to the feedback between clouds and radiation. Essentially, the presence of upper-level clouds that develop in moist environments increases tropospheric radiative heating because less long-wave radiation escapes to space. The additional diabatic heating supports additional vertical motion, which transports even more moisture to the upper troposphere. This is part of the growth mechanism of the moisture wave, and we can see that as the gross moist stability ends up showing up in the imaginary component of the dispersion relationship. The dispersion relationship is denoted by the curved lines that correspond with the power at low wave numbers and frequencies for eastward propagating disturbances, as shown here. The phase speed of the moisture wave is always toward the east, while the group velocity is toward the west. These plots show Hofmahler diagrams of actual bandpass filtered OLR anomalies in the MJO, with time increasing going up on the plots. Again, these are derived from observations and reanalysis. The green areas denote OLR minima, and they are propagating toward the east. However, the apparent energy in this mode moves toward the west, which is also clearly seen in this plot denoted by the negatively dashed sloped lines, or negatively sloped dashed lines. A study of successive MJO events, meaning those that are immediately preceded by another MJO event, shows that the MJO propagates over the Indo-Pacific at the theoretically derived phase speed, as shown before, but more like a convectively coupled Kelvin wave over the Western Hemisphere. The blue shaded regions in these plots, separated by time of year, indicate anomalies of column mean latent heating in an equatorial wave, shown again on a Hofmahler plot, now with time increasing going down. Several MJO events were composited together to create these plots. The x-axis spans the entire globe, while the y-axis spans about 60 days. The purple line starts from where this blue shaded region is at the date line on the left side of the plot, and it outlines the track that the blue shaded region, which is essentially the upward branch of the MJO, would take if it had propagated like a Kelvin wave coupled to diabatic heating anomalies associated with latent heat release and radiative cooling. The orange lines show the propagation of the MJO if it were a Kelvin wave where convection were not active, so like in places like this, and here, the orange line tends to be parallel to the purple line, but as a moisture wave where convection was particularly active, such as this location right here. Clearly, it agrees very closely, the orange line does, with the blue shaded region, which is the actual track of the OLR anomaly. So this provides some evidence that perhaps moisture mode theory is applicable. However, numerous other theories exist that can also explain some of the salient features of the MJO that were described at the beginning of this module. All capture the eastward propagation of the MJO in some way, but the fundamental dynamics in each theory are different. One theory, the gravity wave theory, for example, does not even require moisture to describe the eastward propagation. Each theory, including the moisture wave theory that we've shown a few slides about, has its own sets of assumptions and limitations, such that no theory is widely agreed upon and accepted. A combined theory that explains both MJO initiation and propagation continues to be an active goal of tropical meteorology researchers.